Welcome, everybody. Ooh, come on. Welcome, everybody, to our 6th visualization night. My name is Travis Gorkin. I'm an engineering manager here at Uber on the visualization team. Like I said, this is our 6th visualization night. We started this meetup group, this series, back in 2017. We've held these in 3 cities. We're back here in San Francisco. Really excited about the turnout, the crowd, the pizza. Everybody, thanks for coming. So I hope you all enjoy the content of the presentations tonight. Really quickly, I'll just give you very brief background into the Viz team and the theme for tonight's evening, and hand it over to the presenters as soon as possible. So the Viz team, really quickly. We're a team of about 40 engineers, an incredible group of 40 engineers. I think we have pretty diverse nationalities and backgrounds. We've got people who have backgrounds in information design, traditional software engineering, web development, computer graphics, game development. We even have 6 former architects, like the kind that design buildings, not software. So it's awesome. It's a great group. I'm blessed to be able to get to work alongside this group. In terms of what we do, our core mission is really to build tools to provide insights into data. We're building software frameworks and tools that visualize huge data sets in browsers. So a lot of that data is geospatial. Almost all of the tools and frameworks we build are open source. We love open source, big believers in open source. So we have lots of different tools and frameworks. Go check them out. Deck.gl, Kepler.gl, ReactMap.gl. These are all like web-based frameworks for building really powerful data visualization applications that run in a web browser. So here's some examples of Deck.gl stuff, some Kepler.gl stuff. Go check them out. But we also do stuff that's more about advanced business intelligence, machine learning visualization. But really the theme for this evening is around autonomous visualization and mapping. And we've got 3 awesome presentations tonight on this theme. So I'm really excited about this theme. I just want to give a very brief little bit of kind of context about how we think about autonomous visualization and why it's really important. So in maybe a traditional application for data visualization, the visualization piece sort of comes at the end. Maybe you are visualizing a bunch of data that has been transformed through some pipeline and trying to summarize it in some nice way. For autonomous vehicles and self-driving vehicles, like the 3D visualization is what you start with. It's kind of the core of the concept here. So it's really interesting to kind of turn it on its head in terms of how we think about this stuff. There's a lot of use cases that are probably obvious around visualization and mapping for autonomous vehicles. But we here at Uber have a whole division working on self-driving vehicles. And when you start to think about autonomous at scale and operationalizing it, there's a whole bunch of applications or use cases for visualization and mapping that maybe aren't as obvious, but are just as important. So just to kind of warm the crowd up about and start thinking about these contexts while our presenters are talking more about some actual real world applications of this. So, I mean, the obvious use cases for visualization mapping would be maybe you have autonomous engineers debugging the sensors that are perceiving the world around the self-driving vehicle. Real-time operators of the vehicle maybe monitoring that and controlling it. Capturing all that data, you might want to look at it in terms of logs and play back those logs. When you start to look at those logs en masse and at scale, you start to analyze them and triage those logs and triage specific situations. All of these things are kind of the common maybe use cases that jump to mind when we think about autonomous visualization. There's kind of a whole second order of use cases that I start to think about, and we start to think about in terms of high definition mapping And we've got folks here from Mapbox who are going to go deep into that, mapping and vision and labeling. And then what's increasingly become a key part of developing autonomous technology is simulation. Visualization and mapping are a key part of this. And then you get to, when you start to think about operationalizing and productizing an actual self-driving vehicle, which we'll see how far we are away from that. You start to think about, you need visualization. If you're going to build any type of thing around remote monitoring and assistance of a vehicle, maybe you have a whole fleet of vehicles and you need to manage them and observe them. There's visualization aspects there. Then you start to think about, okay, we're going to do this. There's going to be government agencies and transportation agencies, and we're going to need to collaborate and communicate with them about how vehicles are working in their cities. And there's a whole aspect of visualization that's important there. And then there's probably a whole ecosystem of developer tools. And so that kind of leads into some of the talks that we're going to hear about tonight. So those are all kind of maybe the second and third order aspects of visualization and mapping as applied to autonomous. But kind of the most important case is not really technical, but it's worth thinking about, is that for self-driving vehicles to really become adopted by the mainstream, for public perception to really embrace self-driving vehicles, they need to understand them better. And they're not going to go check out the source code and dig in and understand how an autonomous vehicle is behaving in the world. They need visualization and mapping tools to be able to understand that. So the whole theme for this evening is around autonomous visualization and mapping. And the fact that that aspect of it is going to be so important for the public to be able to just understand this technology and embrace it. Not just the public, government agencies and transportation decision makers, I think makes this a really sort of important concept to be talking about. I also think that an ecosystem around this is inevitable. There's a lot of companies that are working on different products, different pieces of technology, some of them open source, some of them closed, but it's inevitable that there's going to be an ecosystem of stuff about this. So gathering here tonight to come and learn about this, gathering great presenters here to come talk about this is really helping and maybe set some of those early steps towards creating the ecosystem and accelerating the ecosystem of visualization and mapping around autonomous vehicles. So you can do your part by tweeting anything you like with the hashtag #UberAutoViz. Start accelerating the ecosystem. So brief overview of the agenda tonight. We're going to have 3 presentations with presenters from Uber, Mapbox, and Cruise. So first, I'm going to hand it over to Tim and Joe from Uber to talk about AVS Auto. Thanks, everybody.
I'll take the clicker. Hello, everybody. My name is Tim Wojtaszek. I work on the Uber visualization team. And this is Joseph Lisee. We're both senior software engineers. He's on the autonomy side, and again, visualization. So let's get into Uber's autonomous visualization system. So first, at Uber, we ignite opportunity by setting the world in motion. The Uber visualization team empowers creators with cutting-edge solutions for solving urban mobility challenges. And in the context of tonight, we're solving it with robots. So here's a quick overview of what we're going to be covering. First, just what is AVS, and then the components that make it up, xviz and Streetscape. And then we're going to go into like how we build Streetscape, the kind of technology layer. And then we're going to give examples of some of the applications and follow up with where we're headed next. And from there, I'm going to pass it over to Joe, again, senior software engineer, the creator of xviz.
Thanks, Tim. All right, next slide. All right, great. So first we're going to talk about what is AVS. Basically, it's the autonomous visualization system is an open standard for describing data from autonomy systems. That's the world around the vehicle, the kind of plan, where it's going to go, what it thinks objects around it is going to do, various kinds of metrics about itself and those objects, and it's a toolkit for visualizing that data in the browser. So as kind of Travis mentioned, we look at this as a new space. Just like in the web, you have kind of clients and servers connected by protocols. we think there's an emerging space for kind of complex autonomous systems where there's going to be various clients and protocols that connect them. So we have the xviz protocol that kind of describes all this data. And then we have the Streetscape, which is a toolkit for building clients to look at this data. And so we think by kind of open sourcing it, we'll be able to build a kind of ecosystem of compatible clients and servers. And we'll be able to incorporate the best ideas to make like what we're building even better. So what exactly is xviz? So xviz is a specification for describing the world around an autonomous vehicle kind of as it changes. So you can describe the objects with various geometry primitives like polygons and lines and point clouds. You can describe the properties of those objects like their velocity or their class or of the system itself, like its velocity or various performance metrics. Then you can also describe how you want to visualize that data with user interface components. And so a key bit is that part is sort of like HTML, but it's also like a video file in that all of the data is divided up into streams and it's time-based, so that you can represent a world kind of as it changes over time, which is how an autonomous system is. And then you can associate all those variety of data streams with certain objects in the world, which I'll get into later, and you can style them, so you can kind of make them look appropriate for the domain. And then to kind of bundle all that together, we've defined two main protocols that define the data: an easy-to-use JSON format and a more efficient binary format. And then we kind of have a defined system for how an xviz client could talk to like a server. I mean, an xviz client like Streetscape could talk to a server to fetch data, both from a running system, like a live system, or like doing a log after the fact. And so we kind of package all this up with validation and manipulation tools to kind of help you build things on top of this platform. So what does all this look like? So here is our Streetscape demo application. And so basically everything here you see is powered by kind of an xviz data stream. We've got laser point cloud data. There's images up in the corner. There's 3D boxes representing the objects in the scene. There's lines representing the trajectories of the objects in the vehicle itself. And then since xviz data is self-describing, the client here at Streetscape has actually automatically built a UI that lets you turn on and off any part of the display. And then also, it's not demoed here, you can hover over every pixel in that image and it'll tell you exactly what that point is. But if you've ever dealt with a kind of a complex data display and you ever have a question of what is that, with xviz and Streetscape, you will automatically know what that is. So kind of one of the key things, like why would you want to go through the effort and build this abstraction? So what we're trying to do is decouple the presentation from the platform, so you can have people on both sides just focus on what they're best at. So autonomy developers can just build with an API, and they can like focus on their problem domain and describe their data just once. And then application developers can build rich user interfaces that don't need to be constantly updated every time like a downstream system changes. Or you can also take just one definition of data that a developer has done and then render it to a video or display it in a mobile app or show it in a high-performance desktop app as well as a web app. So this lets you build like a specific targeted rendering, like you can focus on building a good rendering experience. And also, like as mentioned, as you get more toward production, safety matters. And these visualizations are actually used in kind of critical areas to decide whether the vehicle made the right choice or for an operator to decide if the vehicle is about to make the right choice in real time. So xviz provides a layer where you can test that when your code does a certain thing, you're going to represent that in your UI in the appropriate way. So kind of how does the flow in an xviz system work, or an xviz-based system work? So you would have a car or you would have a log, and that has kind of raw autonomy data from your system. And then you build a server component that would either run inside the car or it would kind of be an independently deployed service that would get data from the log. And then kind of the raw autonomy data flows from the autonomy system log into a converter. And then that converter uses our builder APIs, which make it easy to create xviz data, to kind of convert all your data. Also, you can use reflection and introspection to kind of convert most of your data automatically, so you don't have to kind of do a lot of legwork. And then the data gets encoded to either a JSON or a binary format, depending on what you want to do in the encoder. And then from there, it can kind of go two places. You can save it off to a log, like you would in Photoshop, like saving an image or a video authoring tool. So you can save the actual visualization like off to the side, and then you can kind of replay it into tools or analyze it later. It's very useful for debugging front-end applications. Or we can use our defined streaming protocol to actually stream the data live to a client. And this could be like a web browser sitting in your car connected to your running system, or it could be like a web browser at somebody's desk kind of talking to a service and they want to view a certain part of a log. And so then it goes through the protocol layer down to a decoder that kind of decodes the data into an efficient format, and then it goes into a buffer. So that buffer is kind of like YouTube. If you ever watch YouTube and you view like a live stream, it's kind of cool. You can go back in time at any point in time. So xviz allows a client to maintain that buffer of the last n seconds of data and jump back in time to look at any bit very, very fast. Or if you're viewing like a log that's hours long, you can just jump to a random spot. You'll load the data just around that portion and then explore that. And that's what the synchronizer does. Unlike a video stream, it's not just a couple audio streams in a video. It's hundreds to thousands of streams. And so the synchronizer gets a coherent view of the world at whatever time you want to view, and then formats that data so it can be rendered in 3D or displayed in 2D controls. So what does that actually look like in a client? And so for that, we're going to go to Streetscape and Tim.
What's up on the screen? I got it. There we go. So what is Streetscape? Fundamentally, we want it to be a toolkit that makes working and using xviz easy. This means it's going to be handling the processing of the data, rendering the data, managing interactions with the scene, managing control of the data through like timeline, forward and backward and such, and then coordinating the data that flows between the components. These components are React-based, so hopefully you have React app. And then it follows an 80-20 philosophy. So we want to provide the components that are going to provide 80% of the application, but for your specific use case, you're going to have to add the 20% on top because there's things we don't know that you may need. So going back to another example of this, I'm going to move from the right to the left. On the top, again, video component. You can see, video component, so you can see the hand wavy talking. So you can see the actual camera frames. Below that's a little customized toolbar, right? So there's going to be camera controls. There's going to be object selection. That would be like a custom component potentially. On the bottom, we have the playback control with a timeline element. And then we're going to move to the left. We have a chart panel. So there's more panels behind that on the top tabs. We didn't see them here, but in this view, we have the various metrics related to the vehicle and data streams. And you'll notice that the chart is synchronized with the timeline in the playback control. And then below that is another custom element, a HUD, critical information you may have in your data system that you want to be always visible. And then you're going to represent it in an appropriate way. Big green for autonomy, gauges where it makes sense to give a relative kind of visual indication. Pardon me. And so that's what it looks like. So why Streetscape? So I kind of think about this as why the web almost. Now, obviously, it's meaningful because web applications are everywhere. And talking about I can't say the word. Operationalization. Well, any case, talking about that word, right? It's available anywhere, point and click, and you get access to the data, right? So with that, you just have to make it performant. Okay, so how do we do this? We do it with using libraries we'll get into in a moment, but the focus here is on building applications, web developers building applications on top of this framework or toolkit. We provide the components you can extend and build upon, right? And then it's a web application. Bread and butter is integrating additional data sets, right? Maps are an obvious example. You can imagine going off of Travis's list of things we need to be concerned about, right? Event data from the past or metrics from the past that compare what you're doing today. And so, again, why Streetscape is because getting all of this together is non-trivial, right? You can do it. I'm not saying it's overly complicated, but if you don't have to do it, that means you can put your effort into features on top. So let's take a look at some of that data. Why is it non-trivial? So I'm going to go from top bottom. The data coming off of an autonomous vehicle has different coordinate systems. You have a vehicle in some reference frame, okay? It's driving through the world, but it has sensors on the vehicle. Those sensor data is relative to the vehicle. So we have some reference frame for the vehicle. We have sensor data relative to the vehicle that we need to get into some kind of transformation pipeline. Then we're going to have geospatial data, a map. Now, you could have things just geospatially done completely, or you can imagine in some data sets, you have like a geospatial anchor, and you have relative offsets to that. So we've got these various transformation pipelines that the data has relationships all toward. and you need to compose all of these into a scene. And so, yes, you can do this. It's possible. Accuracy, you have to go through testing. You have to do all the kind of, dotting the I's and crossing the T's, or you just use AVS. So then on the performance point, how does this work? We need to match near native performance as best we can, so that this is useful and meaningful. And we do it by using our WebGL framework, Deck.gl. So Deck.gl is not a generic 3D framework, or 3D library. It's geospatial optimized, okay? You don't have to worry about, nodes and transformations down the branches. You provide it data, and it will map that data to a visual representation. It has a reactive programming model, if you're familiar with how that works, and it has a powerful layering mechanism so that you can compose multiple layers of independent data into the scene. Perfect for what we just described. So the performance side comes from the fact that these layers are actually done in the shader code. And since it's geospatially optimized, that means we are doing those geospatial projections in shader code. And then, of course, we provide interfaces for hooks for hover and click. So you don't have to think about graphics library. You think about data and what I want to do with it. There we go. So again, this visualization library isn't easy either. And we've spent over 3 years building this for internal tools, both for what you can see a few examples of geospatial and non-geospatial data. And so it's an obvious reason to maybe look into it if you're curious. And the reason for the performance is because you need the front end to be responsive. And so using the GPU, especially when you deal with a lot of data, it gets us where we need to be to build this stuff. Here's a quick, I don't know if it's how visible it is, but these are some of the layers that are just available in Deck.gl. You can see from the top bottom, we have a hexagon layer. We have an arc layer, a circle layer. There's a path layer. And you can see like a GeoJSON layer. There are other layers. I recommend you go check out the GitHub page and see what's available. And there's some live examples there as well. We're going to go through a few canned examples. So in this one, we're looking at like a statistical density representation of 800,000 points. And what's happening is that the geospatial projections happen in the GPU. And you can see the zooming in and out is nice and smooth. Here's an example of where we can provide input to the shader. So the input here is going to be the pointer position. And then we can pass those into the shader. And it can do filtering on the data based on the radius from that point. So this is, again, all done in the GPU. You're filtering in the GPU. This is an example of how we're using the GPU to smoothly interpolate between the vertex colors of over 40,000 or 400,000 points. Okay? We're changing the year, and it can reload the data and do the interpolation on the GPU again. And the last example I have here is where we're doing aggregation in the GPU. So in this example, we can change the grid size, and it's going to be fixed. And then whenever you zoom, you're going to see that it's going to recalculate the bins. And again, this is like turnkey functionality that you're going to get out of Deck.gl. So hopefully that gives you an idea about what Deck.gl is, how and why we use it inside Streetscape, and maybe why you might want to look at it for your own applications. Speaking of applications, I'm going to hand it back to Joe.
Thanks, Tim. So over the past several years, we've been building a complete kind of end-to-end autonomy development platform based on the web at Uber, all the way from kind of triaging events that might have happened in the vehicle to looking at simulation results, to looking at logs, to debugging and map editing, to like labeling data at scale for our autonomous systems. So we're going to look at those applications that are based on AVS, especially Streetscape and xviz. So this is our log viewing application. In this specific application, the objects and the laser data are done through xviz, and the HUD is powered by specific kind of xviz data streams. Then we take Tim's 80-20 philosophy here. The mapping data here is actually done through a custom Deck.gl layer because the data is not well handled by xviz, but because of the composability of Deck.gl, we can just put another layer in, and they work well together. So next, this is an example of what I was talking about, where if you can let teams just focus on their domain, you can create kind of more powerful applications. So this is the same application, but it's in a difference mode. So you can imagine you make a change to your code, you run 5,000 simulations, 20 of them don't work anymore, and you're trying to figure out why. So you can load one up, and you can look at the result before and after your change, and you can kind of compare the differences kind of side by side or over top of each other. And so this is kind of one feature we built into our log viewing tool. And so that kind of helps you narrow down the difference quickly. And as well, kind of on top of that same framework, we've visualized kind of more of our mapping data to kind of so you can gain insight into it. And then I touched a little bit earlier on kind of objects in time, but this is kind of a more concrete example. So here you kind of see a set of cars moving around the vehicle, and those cars kind of have little spark lines above that. So each of those things, like the velocity of the vehicle, the acceleration, its predicted path, the object itself, are all separate streams in X's, but they're all tagged with the same object ID. You might notice that number on top. And so here our log viewing client notices all the data is the same ID, and then it creates a little panel that shows you all the data associated with that object when you click on it. In addition, it can bring up those charts specifically on the side. And so another feature here that I really haven't touched on is that xviz is designed to view kind of time ranges of data explicitly. So some applications might be based on sort of a playback model where you turn them on and kind of hit the VCR button play, and then you hit pause and kind of look at stuff. xviz is designed that you look at a slice of the world and you kind of randomly jump between it and you get a consistent picture. So that lets us create these little charts. So you can see what the velocity is like ahead of where the system is playing, instead of having to wait for it to play and then see what the velocity was at that point. So it lets you kind of build more powerful visualizations around times of interest. So and finally, just like we're trying to do here in the open source world, we've built an internal kind of platform for viewing autonomy data, and we've plugged that into other applications. So here's a shot of our triage application, and that's the same view they would see in the log viewer itself. And also one of the benefits here is actually we have another tab not pictured, which is a video tab, and that video tab is generated from the same xviz data you see here. But the advantage of the video data is it basically, because it's on a CDN, loads sub-second. We work very hard on performance for the 3D application, but it takes a couple of seconds, and that lets people go through hundreds of events very quickly, and then only when they need to see more data do they jump into the more advanced application. But that requires no effort on our part, because users define data once, and then it automatically gets rendered by an xviz-based 2D renderer. So we don't have to kind of manually update two tools every time data changes. So what are we doing next? So next, we're going to be releasing a kind of a complete server example in Node.js. We're going to be releasing raw support, so you can view raw data, convert it to xviz automatically, and then view it in Streetscape. And we're going to be working on persistent data, so we can map data better. And we have an interactive playground we're going to be polishing that lets you play with our API and see the results and kind of paste xviz data in and see what it looks like. And then after that, we're going to be working on point cloud compression, kind of more advanced primitives, and better documentation. And long term this year, we're hoping to get our protobuf support complete, as well as additional languages on the back end, like Python and C++. So thank you.